Okay, so welcome back to the second stage of your inferential testing lesson. So by now you should know that when we are deciding on an inferential test, so we've done our descriptive statistics and we're ready to analyse our data and conduct a sophisticated mathematical statistical approach, that we have to pick a test. There isn't just one test that we do for everything. And we know by now that we have to ask, is there a difference or a relationship? What is our level of measurement and what design is being used? The next step, of course, is once you've answered all those questions, is how do you know which test from a list of options to go for? And hopefully you should see on screen now that in front of you, you have got 1, 2, 3, 4, 5, 6, 7, 8 tests that possibly you could use in order to analyse your data. We've got the sign test, we've got the chi-squared test, we've got Spearman's row, we've got Pearson's product moment, we've got the Mann-Whitney test, the Wilcoxon signed matched ranks, the repeated related t-test, and the independent unrelated t-test. Let me show you a table that you basically need to learn off by heart. And if you walk into the exam not knowing the structure of this table, things are going to be tricky for you. What this slide represents is how all of the information about difference, relationship, level of measurement and design all fit to link up with a specific test that you decide to run on your data. So if we have a look through, at the top of the slide, we've got difference or relationship. So if, for example, we know that we're looking at two covariables, a correlation perhaps, and a relationship, we know that we can ignore all of the data under the difference columns, and we can look straight to our three options under a relationship, which is chi-squared, Spearman's row, and Pearson's. Now, which one of those we pick to run on our data all depends on whether we've got nominal, ordinal, or interval data. A really good time to point out, guys, that in that list of relationship options, Spearman's row and Pearson's are the only two true tests of a correlation. They are the only two true tests of a correlation. Chi-squared is not a correlation assessment. So please don't think that just because a scenario says relationship, that it automatically means you've got a correlation. It could be that it is Spearman's and Pearson's. But if your data is nominal, actually what you're going to run is a chi-squared assessment, not a correlation. So just bear that in mind. If you've decided that you're looking at a difference, then you decide, is it an independent group or a repeated measures design? And then you see, according to that decision making, you end up with the possibility of chi-squared, sign test, Mann-Whitney, Wilcoxon, unrelated or related t-test. And which one of those cells you end up in depends on whether you've got nominal, ordinal or interval data. So you see the idea. We're trying with some challenging yet possible decision making to end up in one of those possible cells to decide which test to do. Now, one top tip, by the way, that students in previous years have used to remember this, so you've got chi, sign, chi, Mann, Wilcoxon, Spearman's, unrelated, related, Pearson's. There is a little saying that students have made up that helps them to remember the order, and here it goes. Carrots should come, mashed with swede, under roast potatoes. Now, I've not gone mad. This is honestly a little saying that people have used to help them remember that order, so it might work for you. So, of course, carrots should come, mashed with swede, under roast potatoes is the first letter of the start of each of the test names, and that will help you to get the order right. Okay, so what do we do next? We've gone through our three decision-making processes and we've worked out which tests we're supposed to be doing. Then what do we do? Well, here comes the next tricky step of inferential testing, is that actually you aren't going to ever be asked to calculate by hand every single one of those tests, with one exception, which I'll tell you about in a second. But what you are going to be asked to do is make judgment of a result from one of those tests. Now, when we're looking at results from those tests, what we're looking for is something called an observed value. Now, an observed value is essentially a result, an outcome, the effect of running one of those statistical tests. And 9 times out of 10, you'll be provided with that result in the exam, and you'll be asked to judge whether it is significant or not. So the question is, once we're given that observed value, how do we know if it's significant or not? Now, you need some understanding, some knowledge, some schemas of probability and significance to make that next step. Probability and significance are all to do with whether the effect, the observed value that we're looking at, is statistically significant. That is it something we're likely to have found beyond the boundaries of chance? Now, if it is, and that observed value that we have achieved from our data analysis from running the test is statistically significant, then that's great, and we are expecting that that effect is beyond error or chance. So what we're looking at here when we're judging that observed value is a p-value for that probability. And p essentially stands for the degree of certainty that the observed value, the effect that we've observed, either being a difference or a relationship between two sets of data, is real, is genuine, is something we believe to be beyond error, beyond doubt. Now, the way in which we measure p is using a numerical scale. And we use a scale that runs essentially all the way from 0 to 1. But we're only interested in a very small part of that scale to make judgment as to whether something is beyond the boundaries of chance. In psychology, we use a p-value, a standard default p-value, and this isn't just A-level psychology, this is in all areas of psychological research. We use a p-value of equal to or less than 0.05. Now, I can hear your brains going, where on earth has that 0.05 come from? It is arbitrary in the sense that it seems quite random, and you think, well, what is 0.05? But actually, let's put it in a little bit of context. All that means is if we're working to a probability value of 0.05, in percentage terms, it means that there's a 5% possibility that what we've observed, our effect, the result of our difference or relationship analysis, there's a 5% possibility that it isn't real and that it's occurred by error or chance. In other words, we're 95% certain that it is real. So now you're beginning to see why we use this standard in psychology of 0.05, because as a kind of standard, we would always, no matter what inferential test we run, we would always want to be at least 95% sure that it's real. Otherwise, it's just too risky. If you're only 92% sure that it's a true effect, that's a bit dodgy. So we work as a golden rule in the area of psychological research to 95%. Now, we see that as an acceptable level of error, in other words. And actually, if we're doing some brand new research, we might want it to even be tighter, stricter than that. I don't know about you, but if a brand new research study is trialling a new drug and is going to give the drug to somebody afterwards, I'd want that research not to be 95% sure that the effect is true. I'd want it to be probably 99.9% sure. So we can move our p-value and we can make it stricter. We can move that 0.05 closer to 0. Perhaps we might move it down to a p-value of 0.02 or even a p-value of 0.001. Now, for example, if we did change our p-value of judgment, how confident we are that our effect is true and genuine, let's imagine we did move it down to 0.02. Then, in percentage terms, we'd be saying that we believe there to be a 2% possibility of error and a 98% chance that the effect is real. So you see the game. It's all about deciding on how confident we want to be. And essentially, the more novel, the more risky the research we're doing, the closer we would want to be to a p-value of 0.001. By the way, we never see p-values of 0. It is silly and naive to think that you would conduct a piece of research where there is absolutely no risk of error or chance. So we only really move down to that right 0.00001. We would never see. And if you see adverts on the telly where they've tested out new substances and things, it will always say 99.99999. It's never 100% sure, because of course there's always a risk of error. So far in this second stage, you have learnt about picking a test. We know that there are 8 different tests available. We know that which test we pick to run depends on our decision making about difference or relationship, level of measurement, or what type of experimental design we're using. And we also now know that in order to judge whether our test has produced a significant effect or not, we look at an observed value that AQA give us, and we judge using a p-value whether that observed value is significant or not. So now is a good time to just pause. That's a lot of extra information that's come your way today. You might want to replay this video. You might want to take some additional notes, try and put it in your own words, try and get your head around some of this new content this morning. And then when you've done that, you'll be ready to move on to the next video.